Rated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Good evening, and welcome to Jefferson Lab. Before we start tonight, I want to call attention. If you didn't see it outside, we have an application form for our high school summer honors internship program. If you're currently in high school and want to work here over the summer, grab one of these outside the auditorium and fill it out. The deadline for applications is March 17th, so it's coming up. Tonight's talk, proud to introduce two folks here from Jefferson Lab. Scott Schwahn and Keith Welch, both from our radiations control group. Scott Schwahn is what's called a health physicist, and Keith Welch is a radiation safety specialist. They're here tonight to talk to us about radiation, what is it, and how can it affect me. Please welcome Scott and Keith.
Wow. Great, glad you're here. Are we set? Great.
There we go.
Good. Well, as Steve mentioned, I'm a health physicist. Anybody know what a health physicist is by chance? Except for you? Anyone want to guess? Yes. Yes. Okay. I'll give you a hint. It has something to do with radiation. Yes? Close enough. Good. Health physicist is really no different than what Keith is a radiation safety specialist. I'm here to protect the workers here, protect the environment, and protect the public from radiation. And hopefully I'm doing a good job. So, you want to say anything, Keith?
Yeah. Radiation safety specialist is a health physicist helper. So.
Okay. Anyway, so what we're going to teach you about is radiation. What is it? What does it do to me? But first off, we have to start off with something kind of basic. What's an atom? Okay. And I need some volunteers to you and you, please. And thank you. And you in the white jacket with a Nike stripe on it. Yep, that'd be great. Orange in the back, please. And right there in the blue. And how about over here, this gentleman? Let's see, how many we have? 1, 2, 3, 4, 5, 6.
Got a few too many.
Good. Okay, we got you all. Okay, let's see what we'll do here. I'm gonna let you two be protons, okay? And, good. You're very positive. Okay, I'm going to let you two be electrons. And you two will be neutrons, okay? Now, first of all, I need you neutrons just have a seat right there for a second, okay? We're not going to use you quite yet. And one proton can have a seat, be on standby, and one electron have a seat. Okay, great. So we have a proton and an electron. Okay, so can you come over here for a second? It's kind of right in the middle here. Okay, she's just going to be a proton. She's just going to kind of stand there and, just kind of wiggle about where you are. Good. Now, you'll be an electron, and you're going to kind of orbit around her. So just start walking in a circle around her. Okay, you don't have to wiggle or anything. Just walk, Okay, anybody know what kind of atom this is? One proton, one electron. Good. Hydrogen atom. Okay, y'all are very good hydrogen. Now, let's change the atom. Let's make this helium. Okay, so I'm going to need all the rest of you. So come on up. First of all, all right, stop the wiggling. You're a neutron? and you're a neutron, right? Okay, so why don't you turn back to back. Okay, everybody put your back facing each other, everybody. Okay, neutron here. Lock arms with those two, please. Why don't you come over here? Neutron over here. Over here. No, no, no. Between you two. There you go. Lock arms. Back to back. Okay? Now just kind of, wiggle a little bit. Okay. Electron, please, keep coming around. You go that way. Okay, around and around, just like she is. Okay, now, we have...
That's great, Adam.
We have 2 protons, 2 neutrons, and now 2 electrons. Wait, I'm sorry, I can't do this right. While you're walking, would you kind of just do a little spin? Okay, and maybe you do a little spin. Okay, great, and they're spinning in the opposite direction, so it's perfect. Okay, don't run into each other. What kind of atom is this? Does anybody know? 2 protons, 2 neutrons, and 2 electrons in the back. Helium. Helium, excellent, very good. That's great. Let's do one more thing. I need 1 proton to sit down. Who sat down first? You sat down first? Okay, why don't you sit down for a second. Stay there. And let's see, why don't you sit down too? Okay, now, rotate, please. Yeah, great. You can just walk. You don't have to spin. Okay, yeah, connect each arms. Okay. So now we have 1 proton, 2 neutrons, and an electron. Now what do I have? Still have hydrogen, right. Anybody know what kind of hydrogen? This is called deuterium, okay? This is heavy hydrogen, okay? We need, you're no longer a proton, you're a neutron, okay? Come on up. Why don't you join in the middle here? Y'all aren't wiggling. Okay, go ahead and connect one more time. So now we have 1 proton. Oops, whoops. I just made something that doesn't exist. Anyway, we had tritium before, not deuterium. Now we have something that doesn't even exist. So y'all just go have a seat. Thank you. Everybody give my volunteers a hand. I got carried away there. 1 proton, 1 neutron makes deuterium. And we actually had tritium there for a minute. Now, y'all have heard of tritium? Most of you? Yes? Okay. Tritium is what happens when you have 2 neutrons and a proton in a hydrogen atom. Okay, now you've seen what an atom looks like. Let's get an idea now of how big an atom is. Okay? So I actually do need 2 more volunteers. Please. Thank you. And yeah, at the end, super. Okay. Who wants to be the nucleus? Me. Okay. Now, he's the nucleus. He's going to be the proton and neutrons. Lots of protons, some neutrons. Doesn't really matter. He's going to be the center of the atom. Okay? Now, you're going to be the electron. Okay? Here. Now, I'm not going to get too technical on you because really an electron doesn't really have size. It's a point. But this is about a good representation of an electron. Hold it up so everybody can see it. Okay, good. Now hold it up. Okay, good. I'd like you to walk as far as you think you need to be how far an electron is from the center of an atom or the nucleus. So go up that way, would you? Yeah, just kind of go that direction. And stop when you think you're far enough. Hold it up, yeah. Thanks. Should it? Yeah, it looks pretty far. Okay. Are you going to keep going? Okay, well. You think that's far enough? Huh. Okay, no, keep going. Yeah. Go ahead. Well, all right, stop right there. Hold it up, good. All right. As y'all can see, he's probably a good, 40 meters away? Okay. You think that's far enough? No. Okay. How far do you think he'd have to go to be a real atom? Nag's Head?
Might be where he wants
Not
to
quite
go.
that far. Who thinks greater than a mile? Greater than 4 miles? Greater than 5 miles? Greater than 10 miles. Okay, interesting. He'd have to actually, get your jogging shoes on now. He'd have to actually go 5 miles before he'd be where this atom needs to be. Now, that's based on the size of this nucleus and the size of that electron. Okay, he'd have to go 5 miles before he's the right space. Now, that's a lot of empty space. Most of what you see, most of matter, oh, I'm sorry, please come back, have a seat. You're done, okay? And you can have a seat too. Thanks for your active role. Yeah. Okay, oh, and sorry, give them a hand, please. So as you can see, most of matter is empty space. There's nothing there. It's just a bunch of electrons surrounding a nucleus, which is made of protons and neutrons, and it's mostly empty space. Okay? Now, I'm going to let Keith go ahead and talk some here about what radioactivity is, because that's kind of what we're here to learn about, is radiation. So go ahead, Keith.
Sure, turn that on sooner. Okay. A nice little picture of the atom that we were just talking about. What do we want to do next is look at atoms in general. How many elements roughly are there in nature? 109? Anybody have a better guess or another guess that's different? Yeah, total natural plus what we've managed to make. 109 is a pretty good number, or 114, I've heard that before, but of course we're making some stuff that's pretty heavy now, so it's somewhere around 100 and some, right? If you count the number of protons, you have the number, or you have the identification of the element, and if we graph the number of protons versus neutrons in elements, for instance, we had 2 protons and 2 neutrons in helium, well, we'd just get a 45-degree angle going up like that. But it turns out that in nature, that is not stable. As you get heavier and heavier, what do you have to have more of? You've got to have more neutrons to counterbalance the repulsion of the protons for each other, right? So it's the true line of stability generally kind of tails over like that. But we also know that for any given proton number, let's take one somewhere in the middle here and call it atom X, it has a given number of neutrons in a, if it's stable. And if it's stable, I guess it should really lie here on that line of stability. But what if for that proton number, in fact, it lies over here somewhere with fewer neutrons than it needs, or if it lies over here with more neutrons than it needs? Then what have I got? No longer have a stable atom, I have a radioactive atom or an unstable atom that's going to do what? What do unstable atoms want to do? What does everything in nature want to do? It wants to get more stable. So all radioactive atoms are unstable in nature because of the imbalance in the proton to neutron ratio, and they want to return to the line of stability. For instance, handy-dandy little piece of the chart of the nuclides here, and we talked about, for instance, tritium, the atom of hydrogen 3. And right here at the top here, it tells us a little bit about it. You can tell it has two neutrons and 1 proton because it's hydrogen, if you look at the numbers here. And it also says up here, it says 12.3A, and that means 12.3 years, and that happens to be the what? The half-life of that radioactive species, right? So every radioactive atom has a half-life associated with it that's a particular constant of that type of atom. Now, we're going to do another little experiment here, and we're not going to have a 12-year half-life because that would take us too long, but we're going to probably have a few seconds, maybe a 10-second half-life. What we want to do is try to figure out, well, if we know there are so many H3 atoms out there, what's going to happen to a population of them? Do they all, first of all, when it decays, what happens to it? We said it has a half-life. What does that mean? What is it doing? Well, for tritium, it's decaying by beta radiation emission. And that means that, and Scott's going to talk a little bit more about this in a few minutes, that the process of decay converts a neutron that's in the nucleus into a proton and an electron, and that electron is ejected from the nucleus, And because it turned one of the neutrons into a proton, it now jumps up one number here and becomes helium-3, which is a stable atom. So the question is, it has this half-life associated with it. What does that really mean? So we're going to do an experiment and find out how that works. And y'all are going to be our unknownium atoms with half-life 10 seconds. So what we need you to do is, if you can, please, stand up, everybody in the room. And what we want you to do is make a choice. I want everybody to decide right now, stand or sit. Now don't do it. Don't do it, but decide in your mind, I'm going to stand or I'm going to sit.
And
okay?
if you do really want to just sit down because you don't want to be
standing. If you don't
standing,
want to participate,
don't do that. Okay, just think, stand or sit.
Just take
Give
a
it a
50-50 shot.
chance.
Flip a coin in your mind and decide whether you're going to stand or sit.
Okay.
Okay. So we're going to take now. It's time 0. And we have a 10-second half-life. So what I want to do is during our 10 seconds that we're going to count off here, everybody that decided to sit, at some point during that 10 seconds, you can go ahead and sit down.
I'll do the counting. So just whenever in that 10 seconds you feel like sitting, sit down. People who thought stand, please stay standing. Okay? So ready? 1, 2, 3, 4, 5, 6, 7, 8, 9,
You don't have
10.
to sit down if you thought sit,
Good.
by the way.
Now, if you look around you, not exactly half is standing, not exactly half is sat down. Thank you. Okay? So that's also the nature of radioactive decay. It doesn't always happen half. Let's do this again.
Yeah, now you got to choose again.
Okay, think stand or sit.
Presumably all of you who sat down, stay sitting.
No. All you who sat down, you're no longer radioactive.
You're no longer radioactive. Everybody that sat down has decayed to a stable atom. So the rest of you now have to decide again. In this next half-life, stand or sit. Okay? So go
All right, got it thought? Okay, here we go. Ready? Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not bad. It looks like a little more than a fourth of you are standing.
This is a random process.
Let's do this one more
time. It's not
time.
exactly half each time. So everybody standing again, decide, stand or sit.
Last time here. Ready? Begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, that's not bad at all. Everybody give yourselves a hand. That was great.
Good job.
And everybody decay.
Everybody can go ahead and sit. Okay, we went through 3 half-lives. And statistically speaking, what, 1 over 3 squared should have sat down, right?
8, 1/8.
Sorry.
Should be standing.
Should be standing, right. And we can graph that out. If you had truly been statistically oriented in nature, right? If at time, this is time down here, time 0, and we're going to go 1, 2, 3, 4, 5 half-lives. At time 0, we had some population of 100% of our radioactive atoms, let's say. During the first half-life, how much do we get down to? I didn't count these out. About here, right? First half-life, if this is number of half-lives, this is 1 half-life, 2, 3, 4. We're going to be down to here. The second half-life, how many? Half of that. Third half-life, etc., etc. So what we wind up with is an exponential decay curve. Does it ever go to 0? Not in theory. What happens, though, when you get, in common sense tells us, though, within a population of atoms that eventually there's going to be 1 left if you wait long enough, and that one will probably decay sooner or later, right? This is kind of a neat thing about radioactive material is it does go away. Now what we're going to get back to is a little bit more about the radiation that's emitted from radioactive materials as they decay. So Scott's going to talk about that a little bit.
Okay. Now, when most of you think about radiation, what kind of things come to mind for you? Monsters. What else? Did I hear radio? Microwaves. Sorry? X-rays, good. TVs, bombs, good. Food, good. Therapy, chemotherapy, okay.
Oh, that's a good one.
So, cancer, good. Okay. We have a lot of things that we think about when we think of the word radiation. Most of the public thinks about things like Chernobyl, the atom bomb, cancer. Some people think a little more on the positive side, nuclear power. Okay. All of us are always surrounded by radiation. Let me show you some examples here of what you might find in your household as far as radiation sources go. Okay. This is a Fiesta-ware plate. It's got the orange glaze on it. I think there's one other, maybe the yellow glaze, which is slightly, okay.
Don't have any of that.
We'll demonstrate exactly what is in this that you should think about, maybe be concerned about, okay? Bananas, okay? Chock full of radiation, okay? What's this? Anybody know? No, not just salt. Salt substitute, okay? So what we're doing with this is instead of keeping the sodium out of our body, I think that's what the idea is, to avoid sodium, because sodium is supposedly bad for you. Instead, we give ourselves, let's see, what does it say here? Potassium chloride. Okay, we'll find out about this in a minute. Okay? So, types of radiation. Okay? There are three basic types of radiation that most people are exposed to most of the time. Okay? There's alpha radiation, beta radiation, and gamma radiation. Okay? Who knows anything about gamma radiation? See, I think I saw this when I was a kid. Okay? Bruce Banner, exposed to high levels of gamma radiation. This is what happens. Okay, so that's one possibility, I suppose, or not. Okay, and then of course, the two-headed pig. Okay, that's also what people seem to think about with gamma radiation. Okay, neither one of those were probably caused by gamma radiation. Okay. Okay. First of all, let's look at the different types of radiation and how they can affect us. Okay. First of all, sorry.
The overheads for the types of radiation.
Yeah, that'd be fine. Good. Okay, let's take a look at this plate. Okay. This is an alpha survey meter. Okay. This detects alpha radiation. That's just about all it detects. Okay. It's on. Keith, you want to get the microphone here, and because they may need that. Okay.
Physicist helper. See, told you.
Okay. Well, we're going to expose the surface of this detector so it can actually see the alpha particles. Okay. Now, if you'll just listen, and we'll see what this plate shows us.
It works.
Okay. So we see that there's some alpha radiation coming off this plate. Okay? What do you suppose we need to block out this dreadful alpha radiation? Paper, okay? Let's give it a shot. I just happen to have some paper right here.
Cheated.
Okay?
Here's some even thinner paper.
All right, well, we'll go with thinner paper. Okay?
Maybe it'll work.
Yeah, that works. Okay, so is alpha radiation something that we need to be concerned about if we have an alpha source sitting way over here? No, nothing to worry about at all. It can't get this far. Put a piece of paper on it. I don't even have to worry about it sitting right next to it. Okay? Alpha radiation, go ahead, Keith.
Interesting coincidence. Remember when we built our atom? Built a helium atom, right? Of course, we had 2 electrons. An alpha particle emitted from radioactive material is basically a helium nucleus. it turns out that when we talk about stable forms of matter, the helium nucleus is one of the most stable. It's the happiest combination of protons and neutrons that can exist in nature. So it tends to be something that's emitted very easily from heavy atoms.
Okay. Let's see what else we might have in this plate. We said alpha, beta, gamma. Let's see if there's some beta in here. I happen to have a beta probe. Okay.
Better keep the paper over there so it'll shield those beta.
Say again? Oh yeah, fine. We'll just make sure there's no alpha interference here. Okay. So now we have a probe. Wow. Is that microphone on, Steve?
Probably not.
That's for the van outside.
Oh, fine.
Guys in the van.
Well, they definitely heard it.
Don't know what to do.
Okay. Can y'all hear that? Pretty heavy beta radiation coming off here. Oh yeah, great, thanks. Oh, you're going to turn the volume on, thanks. Okay, a lot of beta radiation. Now, what do you think can stop beta radiation? Any guesses? You're right. How about a piece of plastic? Okay, piece of plastic this thin. Paper certainly won't do it. Piece of plastic will. Okay. So generally, with most sources of beta radiation, very thin metal or maybe some plastic can protect you from the beta radiation. Okay. Let's see if we can get a little.
Anybody remember when we talked about how during beta decay, what happens in the nucleus, that little transition that took place, and what was ejected from the nucleus? An electron that was formed during the decay process. So this beta particle is that electron. It's a high-energy electron that's produced in the nucleus during decay and then ejected because of its negative charge.
Okay. Now, we're still seeing some counts here, and if we listen to it carefully, it's actually doing a rather good job there, or maybe it's the distance. Okay. Gamma radiation will go through a lot thicker material. Okay. It has no charge. The alpha particle has a +2 charge. The beta particle has a -1 charge. The gamma has no charge. It's a lot like light. Okay, you want to put up that electromagnetic spectrum there?
Yeah.
Okay.
This one.
Move this away. Good. It's not perfectly clear.
It's obvious to the casual observer.
Yeah, it's obvious to those of us who work with it every single day. Okay. What we're seeing here is.
Other way, Scott.
There we go.
There you go.
We're looking at another source of radiation here, okay? And it happens to be in the visible light range, okay? Radiation comes in low levels. We have radio, microwaves, radars, light bulbs. People emit radiation. Who sleeps in the same room as somebody else? Okay? Get out quick, all right? You're being exposed, okay? People, light bulb, this is where visible light is, very little bit here. And then you start getting into ultraviolet. Okay, what can ultraviolet do to you? What?
Tan.
Give you a tan. What else can it give you? Skin cancer. Okay. Well, the tan you get comes at a price. Okay. Skin cancer can develop. Then you have X-rays used for medical purposes and other industrial purposes, and then finally getting into gamma rays, which can go through awfully thick material. Okay, very high energy stuff. So we learned a little bit about alpha, beta, and gamma particles. Anybody else know what other radioactive particles that we have around? Anyone? Okay, we also have neutrons, just by themselves, can be emitted. Thank you. Radium or tritium used in the dial of a wristwatch, self-luminous wristwatch. Not all of you, okay? They're older watches. What else? Anybody go camping? Okay. Have you ever used a Coleman or other brand lantern? Okay. Those little mantles in the middle of it that light up, if they have a green band around the bottom, those are hotter than anything else I have up here. Okay. Oh yeah, I forgot to actually show you. Excuse me. Okay, the bananas. This has potassium 40 in it. Potassium 40 is a naturally occurring radioactive material. You have it in your body. You have it in anything that contains potassium. If I put potassium on the excuse me. Okay. No, can't detect it. Let's take a look here. I'm going to just put some of this salt substitute right here in a pile. Okay, don't use this much. Notice that? There's actually a major difference. Okay? So that's just because of the potassium that's in it. Now, we already covered radioactive decay. Let me give you some idea of what we're talking about here on this banana. Okay? Does anybody know how many people there are on Earth right now? Thank you. Good. Okay, so we have 6. 9, 1, 2, 3, 4, 5, 6. We have that many people on Earth. Okay, 6 billion people. Okay? 1 grain of this potassium chloride that I showed you for the salt substitute has, let's see, 1, 2, 3, 5. Gosh, how many did I say? Let's see. 6, 7, 8. It has that many grains of, atoms of potassium chloride in it. That many atoms of potassium. Okay? But only 1/100th of 1% is actually radioactive. So let's get rid of 4 of these zeros. And we'll just add this at the end and get rid of all these. Okay. That's how many atoms of radioactive potassium are in 1 grain of that salt substitute. Okay? Fortunately for us, it has a half-life of 2 billion years. Okay? So it would actually take 2 billion years for half of that to become non-radioactive. It's really a low-level radioactive material. Okay? The point we're trying to get to is you are always surrounded by radioactive material. You eat it, you drink it, you sleep with it, your home brings it in, okay? Comes out of the ground, comes out of the sky. It's a part of your life. There are some people who believe that no radiation is a good thing, okay? That you shouldn't get any additional radiation. Well, I hope those people don't fly in an airplane. I hope those people don't ever go over to Denver. I hope those people don't ever go to Kerala, India, where the background radiation, the radiation you're exposed to all the time, is about 10 times what you're getting here. Okay? So what Keith is doing over there on the other screen is actually measuring the bananas. So we're going to find out at the end here how radioactive those bananas are. We're just going to let them count for a while and see what happens. Okay, Keith, you want to show them about background?
Yeah.
I may have overtalked you a bit.
Oh, that's fine. Okay, we're going to talk about now a little bit about how much radiation people are exposed to in general, and we'll eventually briefly get into some of the concerns about risks from radiation exposure. Unfortunately, that's a subject that we could spend all day talking about, but when Scott just mentioned some of the sources of background radiation exposure, this is sort of a depiction of the average person in the United States where their radiation exposure comes from and how much from each source. And again, this is a sort of a fictional average person who may or may not exist in reality. And you can see the large bulk of it. This, by the way, is broken up into naturally occurring and man-made or artificially produced types of exposure. This is in units of millirem, and we don't need to really even talk too much about what the units are. We can call it milliunits for that matter for now. We can just talk about radiation dose units that way. You can see that for most people, the bulk of their exposure comes from naturally occurring radioactive material that's in the air that we breathe, which is radon gas. And then you have the terrestrial radiation from radioactive material in the soil. Scott mentioned potassium-40 in your body, which is the internal dose up here. We maintain a supply of various radioactive materials in our bodies at all times. Cosmic radiation, which comes from outer space and the sun and the stars. And then this portion down here, which is the artificially produced segment, I suppose. About 25% of our background dose comes from things that we produce. Medical x-rays for diagnostic procedures being the bulk of that. This totals up to about 360 or so millirems per year for the average person in the United States. Now, on top of that background exposure, folks like Scott and myself and a lot of other people also from time to time are exposed to radiation at work, which we call occupational exposure. But we typically don't exceed the background levels. Our doses are typically less than the background, or not much greater than background. So this represents a dose for everyone fairly accurately. But as I mentioned, as Scott mentioned, it can vary drastically around the world and depending on where you live and how you live. Now, one thing we are going to get into a little bit is risks. How much, if I get that 360 some millirem of exposure a year, does that relate to in terms of a risk for, and somebody said it earlier, what's the main thing we're concerned about with radiation exposure we hear about a lot? Cancer, right? This is a way of representing risks from various risk factors in terms of estimated days of life expectancy lost. It's kind of a way to compare apples and oranges by using a common unit. And if you see here, we've got radiation at about background level here, 340 millirem per year. This was intended not to represent the average person from background. This is intended to represent the excess cancer risk for a person. This is 340 millirem per year above background for 30 years of exposure. In other words, some hypothetical radiation worker who might receive 340 or so a year on average for 30 years, and we're assuming that this is above background. Okay, so you can see how these numbers compare with some of the other risks that we had said. We could make a list as long as your arm of risks that you want to choose to compare. And it's kind of interesting, though, that number falls out reasonably low compared to others. And when we're talking about this, you might get the feeling that we're up here trying to tell you how safe radiation is and how it doesn't hurt anybody. Our job is to protect people from the harmful effects of radiation. So we are not trying to tell you that. We are trying to put it in perspective so that
we'd be in business much longer if we could convince you that all radiation was incredibly fearful and that you needed to run away from it. Because our job depends on protecting people from radiation. But we would like to give you a balanced idea of what radiation does to your body. Okay? There are actually these probability charts that you need to be careful when you look at when they're published, because they can be very deceiving. They can have life expectancy as a result of lost as being female, and then they'll have life lost from being male, and they're both positive numbers. What can you do? Okay, so
can't win. You can pick any particular item and compare it to the average population as a whole and compare its risk. And like Scott said, for those comparisons, it kind of breaks down. We use a model oftentimes in radiation protection that's called the linear no threshold model. And what it does is predicts or helps us try to predict the risks of radiation exposure. One of the things you'll hear oftentimes is there's no safe dose. There's no level at which it's completely safe. And you'll also hear things to the effect that we don't quite know what the risk is. And both of those things, when we teach radiation protection, for instance, in our classes here, when we train people, we agree with that, but it's all in how you state that. If you look at dose units again, ooh, that's not very good. I'm going to say that this is 100, 200. Now I'm going to go up a factor of 1,000 from what we were looking at a little while ago. We were talking about millirem. This is rem, or the basic dose unit. And if we look at cancer risk opposed to these doses, by the way, anybody know where we derived the information that I'm getting ready to plot? Most of the information that we know about regarding cancer risk and radiation exposure? What population of people? Survivors of the atomic bombs. Those people were pretty highly exposed. So we have a lot of data. By the way, let me stop myself again and say, what's the background level of cancer risk? We're going to say that it's non-zero. About 15 to 20% of us will die. So I'm going to call this 15%. Will die of cancer. So that's a steady line. It's variable. It's not exactly 15% in any given population, but it varies around that. In a population of people exposed to these various dose levels, what we see is a line or a set of data that kind of goes like this. It disappears in here somewhere. It does something like this. I'm drawing a squiggly line to represent what? Variation in what we've measured. And if you'll notice, it hits somewhere around less than 100 rem or so. It hits the background, and that's what I'm representing there, is that we can't measure excess risk in these exposed populations if their dose is that low. And this is why you'll hear, we don't really know the risk. But what does it tell us about the risk? We don't know it. Why? Because it's very low. Very low doses of radiation are associated with very low risks. And as you go up, those risk values become more meaningful. Our guidance is that we should not even try to apply a numeric value to the risks that are down in this region. So that's the way when we train people that way. By the way, if I were to receive the maximum allowable dose for 50 years, which is 5 rem per year, I'd get 250 rem over my lifetime. That gives me a cancer risk up here somewhere. What that equates to is about an excess risk of about another 10% on top of the 15% cancer risk that I have from being alive. If I smoke a pack a day, how much excess cancer risk do I have? Anybody know? It's something like about another 10% on top of that. So I'm going to go up here and say it's a plus 20%. I'm adding onto my baseline. Here I got plus 10%. So if I'm a pack-a-day smoker, I've got about twice the cancer risk than I do if I get the maximum allowed dose as a radiation worker. So we have to put these in perspective, and that's wise, because most people would assume that a total dose of my lifetime at 250 rem, if they've ever heard anything about radiation, that sounds like a lot. In terms of cancer risk, it's not all that bad. And of course, we have a program that drives us to maintain our doses as low as we reasonably can.
In addition to that, let's try it again. In addition to this, as Keith showed, towards the low dose levels, it's uncertain what happens. As a matter of fact, there are some of us who believe, of us, meaning in my field, who believe that at low levels of radiation, there's actually a beneficial effect. that it may do things such as boost your immune system. Okay, so there's no real definite proof on anything down in those low levels. It's just impossible to quantify.
A simpler drawing of that, I'm sorry,
Go ahead.
could be this. This is what we assume. Even though what we can measure is this, we stop being able to measure down here. So at low doses, we don't know. That's what you hear. We don't know the risk. But here's what we assume, that for some exposure, this is the risk, that it never becomes zero unless the dose is zero, unless the exposure is zero. But as we said, at some point, this data has to be questioned. So we develop models to attempt to estimate that risk, because it is not known very well statistically because it is so small. Some of the models go like that. Some of them go like that. The one we presume and use on a daily basis in radiation protection is this, what I called earlier the linear non-threshold model, and that's what that line represents. What about a model that went like that?
Negative risk.
As dose goes down below some point, that's a negative risk value. In other words, it's beneficial. And there's quite a bit of data to support that. But we don't use that as a means of operation in radiation protection.
Okay, I think we're going to wrap it up at this point. I'd like to open the floor up. Thank you for that
Would like to thank you.
golf applause.
We should point out the graph above Scott's head over there. We did measure our bananas, and we see that there was some measurable radioactivity in the bananas, which is represented by this peak right here on the graph. This is the gamma ray that's emitted by potassium-40.
We're actually opening the floor up for some questions here, so try not to disturb people as you rush out the door. Any questions from the floor? Back in the back. What is nuclear fallout? Okay. Nuclear fallout is what happens when an atomic bomb goes off. Atomic bomb goes off, lots and lots of radiation, radioactive material is produced, which gets caught up into the atmosphere. It can float around up in the atmosphere and then drop down in other places. Okay? That's what radioactive fallout is.
This little chunk right here on this background dose map indicates that includes nuclear fallout from weapons testing back in the 50s and 60s and a number of other. This includes everything that most people think about when they think about radiation in their environment. Nuclear power plants, disposal of radioactive waste, et cetera, et cetera, et cetera. And also fallout from bombs.
Any other questions? Yes?
On the electromagnetic spectrum we had here, where do the alpha and beta particles come in?
Okay. The question is, where does alpha and beta fall on the electromagnetic spectrum up there? The answer is it doesn't. Alpha and beta are particles, whereas the electromagnetic spectrum have to do with waves or photons. Okay, they're not actually classic particles, so it doesn't really fall on there. As far as their energy go, and as far as the damage goes, they'd be up in the X-ray, gamma radiation region, which can be damaging to your body. Okay. Any other questions? Yes?
Colors give off radiation.
I'm sorry? Do colors give off radiation? Yes, they do. Kind of. All of the electromagnetic spectrum that I showed you up there is radiation. Okay? A type of radiation. Laser pointers, it's a type of radiation. Visible light, colors, it's a type of radiation. What we're concerned about in this industry is what is called ionizing radiation. I'm sorry, we forgot to mention that. Ionizing radiation is high energy radiation starting with ultraviolet and getting up higher, X-ray gamma radiation, that can actually knock electrons off of the elements in your body. Okay? So color, it's a type of radiation. It's a good question. It's just not damaging. Okay? Yes? Oh, thank you. Hey, good question. Where's the plate? What is producing the radiation in this plate? These were glazed with a uranium-containing glaze back when they were made. Okay, on the outside of it is a slight coating. These, as far as damage here, I wouldn't be holding it up on my face and so forth if I was concerned about it. Okay, I would not want to use it in my household only because if the glazing chips, then you start having access to the uranium underneath. A kid licks it, and it's not a good thing. You don't want to get, even though alpha radiation isn't a concern from the outside, it's not something you want to get inside, okay? Because then it can irradiate what's inside of you, okay? So uranium. If you have some of these at home, I'd be glad to check them out and dispose of them for you if you'd like. So.
You get $10 for them.
Okay. Yes.
How does radioactive dye used in nuclear medicine affect you, and how long does it affect you?
Good question.
Very good question.
I'm not going to go into the details of it, but I'll be brief. Okay? In nuclear, the question is, how does radioactive dye used in nuclear medicine affect you? Right? Essentially, and there are two types of dye that they use in nuclear medicine. One is actually a radioactive material that they inject into your body, which, for instance, they might inject a what?
Iodine
131. Okay, and it goes directly to your thyroid, and it irradiates your thyroid. Okay, and that is used to try to get rid of cancerous cells in that particular area. It's a targeted nuclide. The chemistry of it is what makes it go into a certain place, and then the radioactive material in it is what irradiates usually a cancer of concern. There's another thing that is not radioactive but is used in nuclear medicine, which is stuff like a barium compound. And that is not actually radioactive. That is that actually stops the X-rays from getting through your body, such that if you have it, for instance, in your intestines, then the radiation goes through you, but it stops it in your intestines so they can image the intestines a lot better. Okay, because it stops it, and sort of like the white part on the X-ray is where the material is. So it's imaging. It's not actually radioactive in that case.
Scott mentioned iodine for the thyroid. Iodine 131 and most of the iodines that are used are very short-lived. We talked about half-life. Iodine 131 has an 8-day half-life. When you combine that with the natural clearance of the body, it's somewhat less than that. I think it's somewhere around 5 days for a half-time in the body. And so your other part of your question is how long does it affect you and that kind of thing. They're typically nuclear medicine exams or treatments and what have you are intended to clear the body quickly so that they limit the amount of dose that you get unnecessarily.
Right.
Another thing somebody mentioned earlier, I heard him say, and I want to make a comment about it. Somebody said chemo when we talked about what is radiation, right? Somebody said chemotherapy. What is chemo? Chemical therapy, right? So when somebody says they went to chemo, they got shot with drugs that kill cancer. How do you kill cancer with radiation? Well, radiotherapy, right? Big doses of radiation that are kind of focused on the spot, the tumor or what have you, again, to kill the cells, because we know that large doses of radiation will kill the cells.
They're both used to fight cancer. They both have similar effects on your body. They can cause you to lose hair and all that other mess. And a lot of times they're used in combinations. Yeah,
they're used
easily
together a lot.
confused. Any other questions?
If anyone
Looks
has any
like-
other questions, please feel free to come on down. Please give Keith and Scott a hand.
Thank you. Keep your eye on the instruments. Don't let them take the bananas.
If you need someone to sign your schedule, your program, please have that done outside. If you have questions for Scott or Keith, please come up front.
Apparently they're outside. I don't know if they have any actual programs.
I don't know.
Ask Steve.